Well, hello everyone. Welcome to another video of History by Podcast. Today I'm joined by Professor Krauss, and today we'll be discussing his book, The Physics of Star Trek. Well, welcome back to the show, Lawrence.
Well, it's nice to be back with you.
Thank you for joining me again. So
It's been a long time since I wrote that book. I forgot that's what we're talking about. It's been probably 30 years since I wrote that book. Anyway.
I want to start off with transporters. I know you talk about all kinds of things in the book, like transporters, obviously, time travel, warp
Mm-hmm.
drive, all kinds of different stuff that is featured in Star Trek. So, does transporters even seem like a realistic possibility, or is this, or is that practically impossible to create based on
Uh,
real
well,
science, physics?
well, it was a transporter that got me to write the book when I started to think about how I'd make one. And the answer is it's science fiction, not real science. There are so many obstacles in the way to transporting people that make it one of the more impossible things in Star Trek. It's it's it, for so many reasons. I mean, I can go into the arguments, I guess, as I did in the book. First off, in order to vaporize someone, if you want to separate them into their individual atoms, you'd have to heat them up to something like 100 billion degrees, and release a huge amount of energy in the process. I think I said something like 100 megaton nuclear weapons explosion when you did that. But and then how you'd get their particles down to where they're going to go is again another issue. There's no way that you could do that. I argued that the way, if you were going to build a transporter, the way I build a transporter is you'd scan them and take all the information that makes them up as a human being. Okay, we'll get to that in a second. But having scanned that, you send the information to some other place and then use atoms that are already there, combine it with the information to make another copy of them there. Of course, that's a problem. Now you have two copies of them. Well, so you now just vaporize one copy and then you have the other copy. But even that's problematic because I can't scan you at the atomic level because of the Heisenberg uncertainty principle. I can't tell what every atom in your body is doing and where it is. Now I could make an approximation of you, and maybe I don't have to know exactly at the atomic level everything about you in order to reproduce you somewhere else, but it would just be an approximation, and I don't know if anyone would want to take the chance to do that. Moreover, if I wanted to try and record all that information that makes you up as a human being at the atomic level, the amount of information would be more. I think I said when I wrote the book, and even after things have changed now, probably you'd have to stack hard drives from here probably to the moon and back at least to be able to get as many hard drives to record the information from a single human being. So the point is that since I wrote the book the first time, although I revised it to include quantum teleportation later on, people have talked about quantum teleportation, which involves transporting the information of a quantum system from one place to another instantaneously, and that's possible, but only for very carefully prepared quantum mechanical states like single photons or pairs of photons, and we're not carefully prepared quantum mechanical states, so we can't do that with us. We're not quantum mechanicals in that sense. So everything about the transporter is problematic, and I'm sad to say, because I as I think I said in the book, I much prefer to take a transporter than planes if I could, but I can't. And I also talked about in the book, one of the biggest blunders from Star Trek was there's a transporter malfunction. See, if you read the Star Trek manuals, they'll tell you they vaporize you, move a matter stream from one place to another, and put it back together again, which, as I say, is possible. But even if you did that, one of their big episodes is an episode where Kirk comes back, and due to a transporter malfunction, he comes back as two copies of himself, the good Kirk and the bad Kirk. And the problem is that, if you're transporting the atoms, you can't do that, which is, how they say they're going to do. You can't just transport the good atoms and the bad atoms separately. So even if you did make a transporter the way they said you make a transporter, you could never have what happened in that episode happen. So anyway, the transporter is fascinating. And as I say, it was thinking about the physics of the transporter that eventually convinced me on a train ride back from New York to New Haven, when I taught at Yale, that maybe I might want to write such a book.
Yeah, and in that episode in Star Trek the original series, the bad Kirk was like from a different timeline, and they happened to be stepping into the transport at the same time. And then in the next
Right.
generation,
There was, yeah. Well, there were two. There was a bad, there was also a separate episode where there were bad and good versions themselves. That came from a separate mirror universe. So that was a different episode. There's one where Spock has a beard, I think, and that's the evil Spock and versus the good Spock. Or maybe Kirk has a beard, one of the two, and that was a separate example of the bad Kirk. But this one was the transporter
yeah,
mouth.
the mirror Spock is the one that had the beard.
Yeah,
Yeah,
mirror
there's
Spock.
also a next generation episode where they're going to a planet, and apparently there's another William Riker there
Uh-huh.
because at some point in the past, Riker was beamed from that planet onto a ship, and as it turned out, oh, there's another William Riker down there because
Yeah.
the transporter duplicated him apparently.
Yeah, I know. Again, all of which is impossible if you're sending the atoms. All of which would be possible if you sent the information, if you could send the information. And by the way, there's so many other things. In order to put the information back together again at the atomic level from a distance of a planet away, you'd have to have a telescope the size of the Earth, or to have a resolving power small enough to be able to put each individual atom where you wanted to put it. So of course, that information could be contained in the data file that you send, but it would be have to be quite a data file. Anyway.
So what about like the way phasers work, like ships shooting each other with phasers in space, and even fighting at this some ships fighting at the speed of warp. Like,
Yeah,
does
well,
that go ahead?
I mean, phasers. I think the idea is that phasers are directed energy weapons. They're weapons that are like lasers, and they wanted to have come up with a nice name, so they made it phasers. Um, and and um, so we can have directed energy weapons, but once again, uh, the, to produce the kind of energies needed to do whatever their standard phasers do would require much more energy than you could generate in a ship, and um, and phasers as directed any weapon should be basically like laser beams, right? And they should travel the speed of light. They should be able to sort of burn things, but but uh, being able to send a directed energy weapon that just sort of blows up a big ship is not what a laser would do, unless you directed a laser towards something that it would itself blow up and heated it up.
Hmm. But now I definitely want to focus on warp drive, because in Star Trek uh they're going at warp speed.
Mm-hmm.
Scotty says things like, we need more power to the engines, keep going, even though in space, I
Well,
mean, the
yeah.
ship shouldn't need to it'll just keep going at the same speed.
Well,
Don't-
yeah, yeah. Well, it depends what warp drive is, right? And once
Mhm.
again, warp drive is an imaginary thing, and on Star Trek they imagine one thing, but you could have. I mean, so warp drive allows you to go faster than the speed of light, which already appears to violate the laws of physics. But you can. But it turns out you can. The special relativity tells you cannot travel faster. Sorry, faster than the speed of light. But that's traveling in space faster than the speed of light. Space can do whatever the heck it wants. So if you can arrange for space to expand or contract, space can expand faster than, or well, contract faster than the speed of light as well. So you could arrange something where somehow you were carried by space to some other distant point if space were expanding very fast. But you'd actually be standing still. The ship wouldn't be doing anything. It would just be standing still in this bubble of space that's expanding. And now the question, can you do that? And the answer is, well, probably not. The laws of physics say you could imagine with a very special kind of energy producing a so-called warp bubble around something that would expand behind it and contract in front of it. It'd be very dangerous for anything in between you and where you were going because it would get squished. But even there, you need a kind of energy that we don't know if you can create. Something that has basically called negative energy. And so we don't know if that's even possible to create on Earth. But even if you could, you'd need more energy than probably available in the galaxy to do such a thing. Okay, so it's not practical from that point of view. Finally, in the end, you don't end up going anywhere faster than the speed of light ultimately, because what you have to do is you have to set up this energy throughout space between you and where you're going. And that takes, so if let's say you want to go 4 light years away, well, at best it would take you 4 years to send energy out in all the right places to be there ready for your ship to do its thing. And then you could say boom, and you'd go very quickly from here to there. But to set things up, it already takes it already takes 4 years. So you could never actually choose to go from one place to another faster than light, because it would take you that amount of time to set up the experiment in the first place. So you don't gain anything with warp drive, even if you could create it.
Now I like to shift to time travel, because there's plenty of that goes on in Star Trek. You got people going really far into the future.
Yeah.
Some people going billions of years in the past. Like Q throwing Picard billions of years in the past to take a look at the primordial soup real fast. Yeah. And time travel in Star Trek seems to be inconsistent, because sometimes for some reason it'll create another timeline, sometimes like in the Star Trek reboot series with J.J. Abrams, or when they go back in time it actually changes the prime timeline for some reason, but sometimes they jump into the mirror universe or some other alternate timeline.
Yeah, the problem with time travel is exactly that. When you go back in time, you automatically create paradoxes. If you could go back in time, because you could kill your grandmother before your mother was born, and then your mother wouldn't be born, and then you wouldn't be born. But if you weren't born, how did you go back in time? And those kind of paradoxes bother physicists as well as everyone else. And so one of the many reasons people think it's unlikely that you could ever arrange something. The point is, given general relativity, mathematically time travel is possible. And because general relativity just says you have a certain kind of energy on the right-hand side of the equations, you create a certain kind of space-time in the left-hand side of the equation. So if you want to create a space-time that involves, time travel involves a closed time-like curve, as you might say, something where you go back and come back to where you began in time, not just space. Well, you can imagine it, but you'd have to have the right kind of energy on the right side. And we just don't know if you can create the right kind of energy on the right side. If you could create a wormhole, as I discussed in the book, you could create a time machine, because a wormhole would allow you to travel in time if one end of the wormhole was moving and the other end was standing still. But the problem is, with normal energy, it's already been shown by Kip Thorne and others that a wormhole would collapse on a time frame. The mouth of a wormhole, each end of the wormhole, would collapse to form a black hole on a time frame short compared to the time it takes to travel between them. And therefore, there are no traversable wormholes if normal matter and energy are all there is. How could you stabilize a wormhole? Well, you could fill it with negative energy. It's the same problem as warp drive in a sense. You could stabilize it if you could produce this kind of energy that would hold a repulsive gravitational energy that would open the mouth of the wormhole. And we just don't know if that's possible. It's unlikely. You can show that under most conditions you can't do it, but we can't prove that you can never do it. But but it is interesting that's, in principle with general relativity, time and space are on the same footing. And if you can travel in a circle in space, you should be able to travel in a circle in time. And as I say, mathematically, you can in general relativity. The question, of course, becomes whether you can in practice, and the answer is we don't know, which is really what I talk about in the new book, in my new book, The Edge of Knowledge, because I talk about the things we at the edge of what we know. And so I actually do treat time travel there as well.
And what about Dyson spheres? Because they did an episode on that in the Next Generation, where apparently some alien civilization built a Dyson sphere around the sun to collect energy from the star. And I know that theory is old.
Well, Freeman
Yeah,
Dyson had lots of crazy
right.
inventive ideas. I knew him well, and he was a very brilliant guy, and came up with creative ideas all the time, most of which weren't practical, but nevertheless. So a Dyson sphere is basically a sphere that's, built around a star that obviously, if it's 4 pi in area, if it contains all the area, it can absorb all of the radiation of the star and then therefore utilize it in some way. We use a very small part of the radiation from the sun, just the amount that impacts upon the Earth, which, by the way, is a lot. It's already 10,000 times more energy than humanity uses in a daily basis. So there's lots of energy in the sun already. And so if you could contain all the energy of a star, then just you'd have so much more than we have, and would allow you, in principle, I suppose, to do a lot more things. But so Dyson sphere was just the idea of basically surrounding a star with absorbers that utilize all of its energy, and some people have argued that sufficiently advanced civilizations would do that in order to be able to do whatever fancy technologies they were involved with. But and so once again, it's not impossible, and it's presumably, it doesn't violate any laws of physics. Again, the kind of energies and technology needed to build a structure that would surround a star is, as we like to say in physics, non-trivial. But it nevertheless could it's an idea, and it's, as I say, Freeman came up with the idea. It's not practical, but it's not impossible either.
Hmm. And when they travel, obviously going back, this is kind of going back to the topic of warp drive. When they travel to other star systems,
Mm-hmm.
to colonies or to build colonies, um, do you think that it is possible that humanity in the future will develop some way of going faster in space so it doesn't take as long to get there? But I know you also said that we can't really go faster than light.
Yeah, I don't see any likelihood that that's possible. I mean, even traveling near the speed of light is going to be is daunting, just because mass is the enemy of space travel, and so you might imagine sending a light ray, but sending a person or even a small object requires a lot of energy, and so the speed of light really is, for all intents and purposes, a practical limit. Unless you can invent wormholes. But then, if you can invent wormholes, you can do so many other things because you need this weird kind of energy. But assuming you can't find shortcuts through space, which again seem extremely unlikely because of what I told you, that you can't traverse them unless there's a very special kind of energy holding them open. Barring that, speed of light is the ultimate speed limit, and that's why I think it's imagining spacecraft zooming around the galaxy at near the speed of light is just ridiculous. The energies required are immense, and why would you want to? So, other than have a neat TV series,
Hmm.
and so maybe we'll send out some large ships that are large enough to somehow survive lengthy periods in space. I can't imagine that again because there's lots of radiation. So we send large groups of people out slowly to on some voyage, one-way voyage to the stars if the Earth becomes uninhabitable or something like that. But it's the idea of zipping around the universe with starships is just not going to happen. And as sad and unfortunate as that is for people who love Star Trek, it's just reality.
And what about shields? You know, when they say to turn on those shields when they're about to get into a fight in space, or turning on shields for some other reason.
Yeah. Well, you know what if you if you read the Star Trek technical manual, which maybe you have, I don't know. Most Star Trek aficionados have it. Anyway, so what they say is that the shields are sort of gravitationally are gravitational devices. Basically, they deflect any incoming energy by bending space away from the ship, if you want to think of it that way. The problem is that it takes an immense amount of energy to bend space. So the sun is 1,000,000 times more massive than the Earth, and the sun bends light by far less than a degree when light goes around the edge of the sun. And if you wanted to bend something like 9 degrees, you need a mass comparable to the mass of the sun, contained in a region that's much smaller, almost like a neutron star or a black hole. And so using gravity to deflect things is probably the worst way possible to deflect things, because gravity is the weakest force in nature. It's so weak that it only operates on scales of planets and stars, and on our scale, on your scale, and my scale, what's relevant is electromagnetism. It's what's holding me up in my chair and what's allowing you and me to talk. And so electromagnetic shields, well, it depends upon what the incoming device is. Again, you can't. You can imagine, putting out electromagnetic impulses that would fry the circuitry of some incoming device. It wouldn't stop it hitting your ship, but it wouldn't explode. But having complete deflector shields, just again, not going to happen. If you could build a physical shield that was strong enough to survive an explosion, that's one thing. But having some force field in space that does it, as I say, the best we can do is electromagnetism. And depending upon the nature of the incoming object, you could imagine having something that either impacted, or if it was metal and you had a huge magnetic field. But again, the amount of energies that would be required would be kind of prohibitive. As they are, let me just say, even under warp drive sounds nice, but even impulse drive, which is less than the speed of light, is already requiring far more energy than you can imagine. To take a small object and accelerate it to half the speed of light and then stop it, using conventional rocket fuel, for example, would take more fuel than there is mass in the entire universe. If you did better still, I mean, the best you can ever do is matter, antimatter. But even if you brought along a lot of antimatter, you need something like 10 times the mass of the ship in antimatter every time you want to start and stop and go to half the speed of light and stop again. So it's even getting to near the speed of light is itself energetically prohibitive. And if you're going to propel the ship using fuel aboard the ship, it's this famous rocket equation that basically says, well, you've got the fuel and then you've got the ship, and you've got to propel the ship plus the fuel, you see, especially if you want to come back. And so you have to put more fuel in order to accelerate the ship and the fuel, but that requires more fuel still. And you find out that in general, the amount of fuel you need if you want a round trip mission and you're going so fast either way is just prohibitively large. One way it's not so bad, but every time you want to stop and start, you're going to have to find a lot more than the mass of the ship in fuel. And that's a challenge if you're traveling through the galaxy.
And what about the cloaking device?
Well, again, that's in some sense more realistic, right? We already have cloaking devices called camouflage, right?
Right.
And when I wrote the book, there was a famous house in California. I don't know if it's still up, but then it's a lot easier to do now. That, the front of the house, I think, was TV screens. Now it'd be CRT. It'd be, It wouldn't be cathode ray tubes; it'd just be LCD panels or whatever. And the TV cameras behind the house, and so it projected the image from behind the house into the front on the front of the house. So it looks like you don't see the house. It looks like you're looking through through. Now that would work, and at least to camouflage you, but it wouldn't. But I'd bounce things off if I were shooting a radar beam or any other beam at it. I'd bounce off and tell me there's an object there, right? Now you can do things that confuse radar, scatter radar, to try and cloak objects and make them less easy to see under radar. And you can imagine doing that. And you can imagine even devices that basically don't reflect radar or light of a certain frequency. They bend it around the object or something like that. And you can imagine that, but only for a very specific frequency of light can you do that. So the bottom line is you can camouflage, but in terms of not being detectable by any kind of measurement technology, that's much more implausible. Moreover, there is the point that physics is a two-way street, and if I can see you, you can see me. If I can't see you, generally, I mean, if I can't see you because you're around the corner, then you generally can't see me. And so if I were going to make a complete cloaking device that just didn't absorb any electromagnetic radiation, let it go around, put it around it and back, well, then it wouldn't be able to see, and you wouldn't be able to see either, right? Because that's the way you see, is you absorb electromagnetic radiation. Or your detectors wouldn't be able to see because they'd absorb electromagnetic radiation. So even if you could develop a device that somehow made you and your surroundings invisible and wouldn't absorb any electromagnetic radiation, you have the problem of that's the way we actually learn about the world around us. So you'd be blind at the same time.
So you figure somebody used a cloaking device that was pretty much as advanced or close to the level we see in Star Trek, the person inside the cloaking field would also not be able to see.
In principle, yeah. I mean, right? Because, the point is that you could imagine maybe allowing, a small hole, that allowed you to detect some small percentage of the radiation and would reflect so small a fraction of the radiation that the distant observer might not see it. So maybe there'd be, you could have little pinholes, but in general, if you had something that effectively makes you not interact, makes you invisible, and it's not just cloaking devices. There are other examples from Star Trek, and one of the examples I think I talk about is an episode called Out of Phase, where Geordi and Ro get put out of phase with normal matter so no one can see them and they can walk through walls and everything else. That has a huge number of problems. But the bottom line is, if no one could see them, they couldn't see anyone else, right? If light traveled through them and didn't get absorbed, then they wouldn't be able to see, because that's how we see, right? We absorb light.
So do you think that space battles are possible at all? And would they look, I would imagine they would probably look very different from what we see in Star Trek.
Well, I know what you mean by space battles. Would it be possible for ships to fire things at other ships? Of course. Lasers. Well, you've got to remember, in space, the other thing that is kind of unrealistic is that, when you shoot something, if it's got enough momentum and energy to do significant damage to a distant ship, well, you're going to recoil. And so if you sent something out that had effectively the same energy as the ship and probably the same momentum, the ship would recoil back very fast. So there's no just sitting there shooting these things and not moving. But beyond that, they wouldn't look like they do I'm sure in Star Trek, because for one of the reasons, not only in space can no one hear you scream, so there wouldn't be explosions, because there's no atmosphere to carry sound. Is a wave, a matter wave, and it requires some matter to vibrate. And if there's no matter, then there's no sound. So you wouldn't be hearing these wonderful explosions in space. But you wouldn't also generally be seeing a lot of fire unless there was oxygen around. to burn things. Now, if you're blowing up a ship, and there's oxygen on the ship, then it can combust. But just out in space, in general, things are not going to combust the same way because there's no oxygen to allow combustion. So you've got it. You can imagine battles in space. It just wouldn't be cinematically as attractive as what you see on the screen, as always.
Do phasers at all, like, I just wanted to go back to the topic of phasers just real quick. Do phasers seem realistic at all, or is this just like too much
I don't
of
know what a
exaggeration?
phaser. I don't know what a phaser is. I know of a laser. I know I can have directed energy weapons with lasers, and a phaser just looks like that to me. So, I don't. So when you ask me, are they real? Well, if they're lasers, yeah, they're real. If they're not lasers, then I don't know anything else that travels at the speed of light that is directed, except for light. You can imagine matter beams that you travel very near the speed of light. So I could send a beam of electrons or something else. I'm not sure what the point would be versus sending a laser. So the bottom line is directed energy weapons are certainly possible, and people are talking about them as anti-satellite weapons, for example. But a phaser is just something that sounds like a laser that gives them the opportunity to have something that'll not just burn things, but suddenly blow up or stun people or do whatever it wants. And that, again, a handheld device that's going to allow someone to, shoot someone and push them back. Well, you're going to be pushed back again. It's not as if you can hold. Anyone who has a shotgun knows what it's like to shoot a shotgun. You get pushed back, right? And that's just normal little pellets. If you wanted to send something that had a million times more energy and momentum, you'd be thrown back at pretty damn fast rate. It's simple conservation of momentum, and that there's no avoiding that with advanced technology.
And what do you make of tractor beams? This, that thing that laser.
Yeah, well, again, a tractor beam. Think about it. The tractor beam is like a rope, right? So it's just a rope using gravity. Well, again, to have a gravitational field that's that attractive, you'd have to have a huge amount of mass and energy. So that's nonsense. But the problem is, it's just like a rope, right? So if you're in space and you try and pull a moon towards you, let's say, okay, what happens with a rope? You pull. What you find out is, hey, the moon isn't moving, but you're moving towards the moon, right? Because the moon has more inertia and mass. And the same thing is true whether you use gravity or anything else. If you're pulling an object in, you're going to, in space where there's nothing to, anchor yourself on, you're going to be pulled towards the object as much as it's going to be pulled towards you. And I don't understand why you'd want to use gravity rather than just a simple rope.
What about the ability of like moving suns, planets, and moons? Because they talk about in Star Trek, the Next Generation, the Iconians, I could move solar systems apparently.
Well, I think moving planets is actually in the long term not only realistic but advisable. I'm just going to put my fan on. It's hot here. Hold on. Because as I say, in about 2 billion years, the Earth is going to the sun is going to be about 15% brighter, and that means that the Earth will be in a region of the sun that's comparable to the region where Venus is right now. And that means the Earth will eventually, the water on the Earth will evaporate. The Earth will become about 1,000 degrees hot. It won't be a very pleasant place to be. And I'm saying that as someone who lived even in Phoenix. So, but even compared to Phoenix, it won't be a pleasant place to be. So we have a solution. We either leave the Earth in 2 billion years, or as I suggested, you could actually move the Earth. You could move the Earth, actually. It was Gerard Tufte, the Nobel Prize-winning physicist, who first suggested this to me. If you could redirect comets or asteroids towards the Earth, but just miss the Earth by a little bit, then you can exchange gravitational energy with the three body systems, and you can move the Earth out slowly in its orbit a little bit each time. But if you have 1 billion years, it's a lot of time. And so by redirecting objects towards the Earth, but not hitting it, you could exchange gravitational energy and cause the Earth to slowly move out in its orbit. And then you see, then if you move the Earth out in its orbit towards where Mars is in 2 billion years, then it would be in a habitable zone again and it'd be okay. So moving planets is not, over long time frames, if you have other objects in the solar system, it's not impossible, and it may be required in a sense as far as the long-term future of the Earth is concerned. But other than that, moving planets and stars is not, I mean, again, they're massive objects. The sun is 1 million times the mass of the Earth. How can you move something like that, right? I mean, you just can't, unless you have an object that's like 1 million times the mass of the Earth that you might want to collide into it. Or you have a conveyor, you have a tractor that's 1 million times the mass of the Earth that, pulls the, I mean, bottom line is it's just basic high school physics that gets in the way.
Well, what about replicators? That thing that can apparently just make food out of thin air.
Well, replicators are apparently just like transporters, but they just use a data bank where instead of having a real person, they have the information of a cup of coffee or a grapefruit or whatever. And well, we already have 3D printers, right? Where you can store information and make something that'll print it. But once again, to replicate something exactly, you have to have, first of all, you have to know how fine-scaled, detailed you need for that. And you have to have the raw materials to create it. So you need the atoms that you can store somewhere, atoms of all different kinds of materials, elements, and then the information needed to store it. So again, it's not impossible to imagine doing that. But you'd have to be able to have a reservoir of atoms and information that was large enough and comprehensive enough to allow you to replicate anything. Once again, if I want to replicate a cup of coffee, I need hydrogen and oxygen. But if I want to replicate a spoon, I need iron and steel and maybe aluminum, and so I need those. You can't create those atoms out of nothing. Well, you can, but even that would require huge amounts of energy. So bottom line is, I can imagine a replicator being like a 3D printer with a storehouse of, other than plastic, a storehouse of other kinds of atoms that you could manipulate with careful atomic force microscopes. But that technology, again, allows you to do it atom at a time. And building something one atom at a time is pretty darn slow, because there are 10 to the 23 atoms or 10 to the 24 atoms in each gram of material in your body. And if I moved 1 billion of them every second, it would still take longer than the life age of the universe to move a gram of material, atom by atom.
Would it also be would it be possible for like a ship to like go next to a star to try to recharge some of their energy cells? Or is
Well, I
that
mean, you don't have to be next to the star. If you go about halfway between the Earth and the Sun, you get 4 times as much energy, right? And I mean, it's a long way to go just to get 4 times as much energy. But the closer you go, the greater the intensity of the radiation. But of course, the greater the intensity of radiation, the greater the need for you to dissipate most of the energy that's coming on the ship if you don't want to heat up and melt. So, not right by a star, but if you could have a large panel that would protect your ship and absorb energy without melting, then you could go relatively close. And by relatively close, I mean 10 times closer than the Earth. But costs a lot of energy to do that. Probably a lot easier just to carry the fuel with you.
I'm kind of going back to the topic of phasers, but also crossover transporters. Just this really strange Star Trek Deep Space Nine episode where this Vulcan dude on the Deep Space Nine is going crazy, and he's using this phaser sniper rifle thing that can beam. No, I think it's actually using some kind of bullet actually. And it's beaming the weapon after it fires through walls so he can hit his target. And his scope can look through walls at the same time. It's crazy.
Yeah, you hit it. Again, sure, I can look through walls if I can somehow have a detector that can detect things that can go through walls. Most things can't. X-rays can't go through walls. If you had a neutrino detector, you might be able to, but neutrinos interact so weakly that generally even a detector the size of the Earth doesn't stop any of them. The neutrinos coming from the sun travel through on the average 10,000 light years of lead before stopping. So you need a heck of a big detector to be able to detect neutrinos. So you'd have to be able to detect something that go through walls, and not many things can, and gamma rays maybe, but even that maybe they can't. So it's again the same simple law of physics, that it works both ways. If something happens to me, if something is doing something to me, then I'm able to do something to it. And once again, if I can't see through the wall, if I can't use anything that allows me to see on the other side, then I can't. Then there's nothing from the other side that's going to get through to me. So very energetic cosmic rays can get through. Very, very energetic cosmic rays can get through walls. And a detector of very, very energetic cosmic rays would be able to detect those cosmic rays, but those cosmic rays would go through any other object. And so you wouldn't be able to see an object on the other side. You'd just be able to detect the energetic cosmic rays, which we do with our particle detectors underground.
And so what about them sometimes finding a wormhole or two to get to the other side of the galaxy real quick, like the Bajoran wormhole? Or you also talk about and I think you talk about one of them in the book, the Barzan wormhole.
The Bajoran, I think, yeah. But anyway, but maybe it's Barzan. I can't remember now.
Yeah, this page 40, you talk about the Barzan.
The one where they try and sell it, and
they're competing with other races.
Yeah. So it's the first and only stable wormhole known to exist. And as I said, there are no stable wormholes unless you can find some new type of energy. So they were very prescient when they said that. And as far as we know, certainly wormholes, we don't know of any wormholes. But beyond that, we also don't know of whether it's possible to make any wormholes. And even if you could, you'd have to. You couldn't connect distant points in space unless those points in space were literally, unless there was a curvature that allowed you to connect them. So I mean, wormholes are lovely ideas in principle, but in practice, it's unlikely that they can exist in our universe. And if they did, they wouldn't allow you to create shortcuts to distant places, unless you were able to manipulate the matter and energy in both places at the same time, so to be able to create the wormhole to connect them. So it's a great devices for science fiction, but in the real world, unfortunately, rockets are probably the way to go, which means, as I've said many times in that book and other books, which is why I think sending people into space is kind of a ridiculous waste of energy and time. It's better to send robots or small things, because matter is the enemy, as I say, of space travel. And so if you want to send objects at far distances very fast, send really small objects like little microchips that can build something when they get there. But humans are 200-pound bags of water that mostly can't exist very well outside of the environments of the Earth.
When do you think like the technological level will make it at least somewhat easier to traverse through space, so we could send people up to other planets and for long-term trips?
It's just there's nothing. I remember Elon Musk once said to me when he gave me a tour of SpaceX, it's not rocket science. And it really isn't. I mean, it's basic, simple physics that is the roadblock to moving large amounts of mass. We are developing propulsion technologies like electromagnetic propulsion or electrostatic, high temperature electromagnetic propulsion, where you heat something up and you send particles out at a very high speed behind the ship, behind an object. Those will allow you to allow small objects to eventually accelerate to fairly high speeds, so they could get to a planet instead of like Mars right now takes 6 months to get to by normal rocket. You can imagine something that would allow you to accelerate over a period of a month, so you take another month to get there. You have to slow down as well. But so we're developing propulsion technologies that allow you to take small objects and accelerate them slowly over time, but keep accelerating them, so they eventually are going very, very fast, much faster than current spacecraft can travel. So I think we'll develop technologies that allow us to send robotic devices very fast to the outer solar system. But humans, as I say, the problems with humans is keeping them alive, and not just going fast, but avoiding radiation on the way, so you don't die of cancer. So I think that it's just a matter. It's going to be a matter of brute force and money to send objects to Mars, and it's going to cost an incredible amount of money. It's going to be incredibly dangerous. A lot of the times things will fail. We can send, as I like to say, we can send a robot to Mars for about the same price as making a movie about sending a human to Mars. And whereas, a human mission is going to cost $100 billion, probably at least. And, and space, no matter what Elon Musk thinks, I think, that's not going to happen for some industry. I think the only kind of group that can do that kind of thing is governments. They can afford to spend that money over long periods. And it's going to be hard and slow and time consuming and expensive. And but maybe we'll want to do it. But I don't think there's going to be some technological magic silver bullet that's going to change anything and suddenly make space travel even in our solar system easy or cheap. Around the Earth, yeah, because going around the Earth is not, we know how to do that. But the energetics of traveling through the solar system are such that if you want to send massive objects through the solar system, it takes a lot of fuel, a lot of energy, and a lot of money. That's just a basic, as I say, it's not advanced physics. It's not physics 401, it's physics 101, okay?
And what do you think of the holodeck and holograms?
Well, as I wrote in the book, I think they're in some sense realistic, in other senses not. I once said, and that was more than 30 years ago, and I predicted it would be at least 25 years in the future, and I don't think there is such a thing yet. We can create holograms, three-dimensional images, and the big problem that having moving three-dimensional images is just computer time and such. So I predicted you'd be able to go to the Paris restaurant, which on the walls of the Paris restaurant will be displayed three-dimensional images of Paris, so you'd feel like you're in Paris. So that's certainly possible, and Disney does it a little bit, right, with moving through holograms. But so that part is realistic. But as I think I said, the best way to do this is not put you inside the scene, but put the scene inside you. So we have these, VR, these virtual reality glasses that give you that make you feel like you're in this three-dimensional image, and that is certainly possible. And now I think Apple's just selling a new one, and other people are, and people who play games can do that, and so that's much more realistic. But putting you inside a three-dimensional scene, well, that may be possible if you have holograms on the walls of the scene, but they're not holograms in the same sense as the holodeck. There's no such thing as holodeck matter. You can't, you could, if you tried to touch a hologram, your arms would go right through it because it's just an image. And so that's the part of the holodeck that's not realistic. But the idea of virtual reality images, well, that's increasing by leaps and bounds. And as I say, right now we can already do that by putting the virtual reality goggles around our head. It's a lot easier than trying to build a room that we walk in. But maybe we'll have a virtual reality room that you can walk in with these 3D images. But all they'll be will be 3D images, and you won't be able to have the kind of interactions that they have in the holodeck. But virtual reality is certainly realistic and happening nowadays.
I kind of want to shift back to space travel in a sense. In Star Trek Discovery, they've got this ship. USS Discovery that apparently uses a spore drive to jump instantaneously in seconds to any point
Yeah,
in the universe it wants to go. Like, obviously, super faster with warp
yeah,
drive. I mean, what do you make of that?
complete nonsense. Yeah, it's complete nonsense. I don't understand it. I don't know. I mean, it just once it gets to the point of technobabble, once they really have this, they start inventing stuff that they it's just words, and the words sound nice, and that's fine. Look, I don't doesn't bother me. I've always said about science fiction, I don't mind suspending disbelief. Um, um, when it comes to good science fiction, it's the stories that matter. If the stories are good enough, you don't mind suspending disbelief about the other stuff. So I don't mind if they imagining that they have something that allows them to do what they want to do. They need clearly the plot needs them to go from point A to B very fast. I don't care if it's warp drive or spores. That doesn't bother me. I mean, it's not realistic, but I don't need it to be realistic. It's the stories that matter, and if the stories are stupid, then it doesn't matter what imaginary technology you have, and you don't want the imaginary technology to be so ridiculous that you can't suspend disbelief. As I said, with warp drive, it seemed okay. I could suspend disbelief. Spores is getting to the edge of where I can say, well, I just can't. I can't watch that episode anymore. But I think that's what I learned as we wrap up in this hour. I think that's probably one of the things I learned when I wrote the Physics of Star Trek. I did a bunch of episodes with some famous science fiction writers, and they pointed out that science is not the key part of science fiction. It's the fiction. If it's a good story, the science doesn't get in the way, and that's what makes good science fiction is good stories. And the technology is nice to imagine, and with Star Trek on this program, I've been kind of poo-pooing things, but what I tried to show in the book is even if Star Trek doesn't work, there are other things that do work in the real world that are more fascinating. And so it's fun to use Star Trek as a hook to talk about the real universe, but that doesn't make the universe of Star Trek possible. It just means that the real universe may be more interesting. That's a good way to sum up and end. I don't know if we're at
I think it was.
Hello viewers, thanks for watching this video from the History Valley YouTube channel. Please don't forget to subscribe and hit the notification bell. And if any of you wish to further support this channel, please consider checking out this channel's Patreon page and becoming a patron, and or donate through PayPal or through Super Chat during your live stream. Thank you.